Okay, the one new piece that I'd like you to learn, what we would have done in Friday's class, is known as Mass Defect. And it's kind of a cool little concept. Back when people first began to work with the nuclei, they noticed something really peculiar. So we know that the mass of a proton is 1.673 times 10 to the negative 27 kilograms. And we know that the mass of a neutron is 1.675 times 10 to the 27 kilograms. So knowing that, we should be able to figure out the mass of any nucleus, right? So, I don't know, if we pick like carbon-14, well, we know that carbon-14 has 6 protons, and that must mean it has 8 neutrons, and so we could figure out the mass of a carbon-14 nucleus by multiplying this dude by 6, this dude by 8, adding them together, and getting the mass of the nucleus. Sounds perfect, sounds normal, sounds reasonable in theory. But when physicists began to do this, they quickly realized that the actual mass of the carbon nucleus was less. And so they began to talk about the mass defect. The defect, meaning mass was missing. What they would have thought in theory wasn't working. So it wasn't 6 times the mass of a proton plus 6 times the mass, 8 times the mass, that really is an 8, I swear, of a neutron to give us the mass of a carbon-14 nucleus. The mass of the carbon-14 nucleus was actually less than this. Okay, so that's what mass defect is. It's like the mass that is missing. So in your notes it simply says, when one compares the mass of a nucleus with the total mass of the individual protons and neutrons that we know are inside the nucleus, one finds out there is a difference between these values, and that difference is called the mass defect. Okay, so it's the difference between the mass of what the nucleus really is and the mass of what it should be if we add up the individual parts. So you'll see this equation. So mass defect is equal to the mass of the nucleus, and that is a misprint right here in your notes, or at least in my notes, so I'm thinking in your notes too. This word should be nucleus, and in mine it's neutrons. If I could actually see it, I think it is. So, and then you have to take away from that the sum of the masses of all the neutrons plus the masses of all the protons. So add those two together and subtract it from the nucleus. When you do this, what you get will always be negative. Okay? Because the individual particles added up will always be bigger than the actual mass of the nucleus. So the mass defect is always negative, and that indicates that mass has been lost. Mass has gone missing. Where did it go? Where did it go? It's a very good question, but you have to wait for the answer. Because before we talk about the answer, we need to talk about atomic mass unit. And you probably heard about this, I would think, maybe in chemistry. We often use atomic mass unit instead of kilograms because it gets really painful to keep talking about the mass of a proton and a neutron to be times 10 to the negative 27 kilograms. And so instead, we switch to atomic mass unit. It's kind of like when we use an electron volts for joules. Okay, so it's just another measure of mass that is more along the size of a proton or a neutron. So it's a very, very small unit of mass used for atoms and molecules, and it's defined, and this is what, I forget who, but one of you might have been you, Sam, or it might have been Justin. It's based on the carbon-12 atom. Okay? So it's defined as being equal to 1/12 the mass of a carbon-12 atom, and that's why the atomic mass of carbon-12 is exactly 12. Okay? And what is an atomic mass unit equal to? 1.660538886 times 10 to the 27th. Do you need to memorize this number? No, sometimes you need to be able to switch to atomic mass units to kilograms, but I'll show you an easier way to do it than memorizing this number. Hey, if you want to memorize one more number, fill your boots, but you really don't need to. I'll show you a way around it. But before we talk about that, we need to go back to where does this missing mass go? Well, so what we now know, or at least believe, is that it's converted into binding energy. It's converted into the energy that actually holds these protons and neutrons together inside the nucleus. Remember, they don't actually want to come together because the protons don't like each other, and so in order to bring them together, some of their mass is changed into energy, and that energy then is used to hold them together. Mass into energy. Hold your breath, because finally Einstein has legitimately brought his equation E equals mc squared onto the board. Okay? So the binding energy is equal to the mass defect. In other words, if you found the missing mass in kilograms, then you can just fill it in here and you will get the equivalent mass in joules out. So if we do that in kilograms, we're going to use E equals mc squared. Okay, so however many kilograms we're missing, multiply it by 2.9979 times 10 to the 8th and get your missing mass in joules. But just a couple of minutes ago, I said this is really actually the amount of mass we're talking about is so tiny that we don't tend to use kilograms, we tend to use atomic mass units. So if our atomic mass unit is 1.660538886 kilograms, we can figure out what's that equivalent to in energy. So take that, multiply it by the speed of light squared, and the answer you get will be in joules to the -10. But again, that's joules, which is big for energy, so let's convert it into electron volts by multiplying by our 1.602. Notice I multiplied by 1.602176 because that's actually a more accurate value for the charge. And since we're trying to get a conversion factor, I used all the decimals here. Your textbook doesn't. It only uses 1.602. So I think it ends up with a conversion factor of 4.9 instead of 4.8. So it's 9.3148 to the 8th electron volts. We tend to write it as mega times 10 to the 6th. So it's 931.48 mega electron volts. So that's for each atomic mass unit. This is our conversion factor, right? So it'll be 931.48 mega electron volts per U. So just like we had joules per electron volt, this will be mega electron volts per atomic mass unit. What that's going to allow us to do is to switch back and forth. So on the next page that you have, with a bug for crawling, the next page you have is to change from atomic mass units to energy. So all you have to do is, if you know your mass in atomic mass units, you could just multiply by 931.48. If you know your mass in kilograms, then you do E equals mc squared multiplied by 2.9979 times 10 to the 8th squared, meters per second squared. So, you have a question. It says the mass of a proton, and they give it to you in atomic mass units. Now, what I used here was the number from your textbook. We actually have a more accurate value, but in most of these questions, you'll be given the mass of the proton, the mass of the neutron in atomic mass units, so that you don't have to worry about memorizing those. You'll be given them. And then it'll tell you the mass of the nucleus, and it'll want to know the mass defect. So mass defect, and I tend to abbreviate it MD, is equal to the mass of